Thank you, everyone, for joining today's CANSSI Ontario Statistics Seminar. My name is Nathan Phelps. I'm a fourth-year PhD student in statistics here, and I'm also part of CANSSI Ontario's Student PhD and Research Network, or SPARC. And part of that role involves helping organize this seminar. This seminar is part of a series designed to spotlight groundbreaking research in statistical sciences, both applied and theoretical, for Canada and around the world. The goal of the series is for participants to engage with leading experts who deepen their knowledge of statistical research. Today's seminar is a collaboration between Western and CANSSI Ontario, which is the Ontario Regional Centre of the Canadian Statistical Sciences Institute. CANSSI Ontario aims to strengthen and advance research and training in statistical sciences by developing programs that promote interdisciplinary research and enable multidisciplinary collaborations. Today, we're lucky to have Dr. Geoff Pleiss joining us. He's an assistant professor in the Department of Statistics at the University of British Columbia, as well as a Canada CIFAR AI chair affiliated with the Vector Institute. His research group specializes in uncertainty quantification and machine learning, especially within the context of Bayesian optimization, spatiotemporal modeling, and scientific discovery. He has also co-founded many widely used open source software projects. So please help me to welcome Dr. Pleiss.
The invitation, Nathan, and yeah, thanks. I'm really happy to be here today and talk about a new line of research for me on what I'm, at least for right now, kind of branding decision-aware models. And I hope that it kind of becomes clear what I mean by this. I would say a lot of the research that I'm going to be talking about here is sort of preliminary in nature, or a little bit kind of case study oriented, where I think what, well, as we'll see, what I'm finding is that there's a lot of room for improving, how we approach modeling in terms of the actual design decisions, model selection, inference, when we know that we're going to be using models in the context of down making, especially sequential decision making. And so these are kind of what I'm going to be talking about today, some vignettes that hopefully help to paint this picture and hopefully inspire you into more about it. So to begin, so I am. Again, my clicker to work. I am a Bayesian at heart. And what does that mean? Well, this is how I like to think about the world. I'm going to start off with some prior belief about, some quantity of interest. And then I may observe some data from the real world. And I then have a nice crank that I can turn to now update what was a prior belief about some quantity of interest into a posterior belief about this quantity of interest conditioned on the data that I have. And all there is to Bayesian statistics is just this crank that allows us to turn a prior belief into a posterior belief with some data. And that's all there is that you need to know about Bayesian statistics, which is, of course, not at all true. If you are actually a Bayesian in practice, and really this applies to any type of statistics, is the procedure from actually going from to producing a model or producing some sort of inference out of a model is a much more complicated flowchart. This diagram comes from a paper that was written by one of my colleagues on what they call the Bayesian workflow. And this is showing the process of what it would take to actually get to the point where you are able to make some sort of model or some sort of inferential or answer some sort of inference with said model. And it's typically going to be this multi-stage process where we're going to start with some potential design space that we would be considering. We're going to run some sort of prior predictive checks. We're going to iterate on our model until we think we have something that would describe the problem we have well, and then we're going to now try to perform some sort of inference and try many different inference procedures and run many sanity checks and posterior predictive checks to make sure that the model is doing what we want it to do. It's quite a difficult process in practice. And of course, this becomes even more difficult when we think about not just using Bayesian inference and our toolkits as statisticians to analyze static data, but when we want to start actually now using these inferences to guide downstream decisions, many of which may potentially yield new outcomes that then influence our model in the sequential process. Right. So often, right, as statisticians, we can focus on, here's the data. I'm trying to do some sort of data analysis. Of course, often, what is the reason that we are doing this data analysis or this inference? It's to inform some downstream decision. When we make that downstream decision, of course, that's going to generate new data, new outcomes that we would potentially want to include again in our model, which would then be used to inform more downstream decisions, and so on and so on. And I would like to emphasize that when we are doing statistical inferences, I like to think of them as an intermediate proxy, not the end goal, because ultimately it's this decision making, or especially the sequential decision making, that often is the goal in many applications. And now, when it comes to thinking about modeling, this actually creates a number of challenges. A lot of the tools that we have developed around developing models, performing model selection within the field of statistics, often these choices are being optimized for inference, and especially inference on static data, not optimized for decision making, especially in the sequential and adaptive context. I think another kind of related challenge is that our models are often assumed to be fixed. Many times when we're thinking about theoretical analyses, we often sort of assume like, here is some model that we are given, and of course we assume, often that our data is well specified or misspecified in a specific way. But in practice, right, our models are not fixed. They're often something that we have to make a set of assumptions. We have to do some sort of selection to arrive at a model that we then want to make inferences with. And this becomes especially difficult when we are potentially refitting our model on more and more data that arrives, especially when this data is adaptively chosen, and not just sort of fixed and given to us at one given time. So what I've been thinking about for the last couple of years, or one of the things I've been thinking about in my research is, again, something I'm calling decision-aware modeling, which is thinking about how will we perform model design and model selection when the statistical model that we want to use is not just going to be used to analyze some static data set, but going to be used to make downstream decisions, potentially in a sequential manner. The setting that I'm going to be talking about today, just to ground things a little bit more, is going to be thinking about statistical models that are used in Bayesian optimization, which is a very common framework used for sequential decision making. For those of you who haven't seen Bayesian optimization before, I'll give a little introduction on what that is. So I'm going to, again, describe a couple of vignettes of ways in my own research on Bayesian optimization that I have found that really taking into account the downstream decision becomes important in thinking about how we want to perform model design and model selection. The first vignette, I'm going to be talking about the geometry of the underlying model that we're going to be using, and how just the simple fact that we are using this model for downstream decisions can have very subtle changes to geometry, can have very disparate impacts on decision making versus prediction or inference. And in the second vignette, I'm going to be talking about a paradigm for decision-aware model selection. So, if we have many possible choices for models, how do we choose amongst them when we know that our downstream, or that our ultimate goal is going to be sequential decision making? So just to briefly describe the setting that we're going to be working in, I mentioned we're going to be thinking about Bayesian optimization, and in particular, Bayesian optimization for scientific discovery. So for those of you who may not be familiar with Bayesian optimization, let's imagine this kind of application scenario. So we're back in grade 6, and we need a science fair project. And potentially what we want to do is what it seems like most people do for their grade 6 science fair projects is we're going to see, how does plant growth, or how is plant growth affected by, some sort of variable. So for example, maybe I have, a bunch of Monstera plants, and I'm trying to see what would be the optimal watering that would make these Monstera plants grow as tall as possible. I'm going to formulate this as a mathematical function. So the variable is going to be, say, the amount of time in between watering. So, it could be, 1 day, 2 days, a couple hours. The scientific question that I'm going to be trying to ask is, what water frequency maximizes the height of this plant? And to now formulate this in a mathematical way, this is an optimization problem where what I'm trying to do is I'm trying to maximize the height function, the height of the plant, which is, again, a function of the variable of water frequency. So, right, this is a mathematical function. It's, of course, not one that we can express in terms of a nice equation that would give us, the ability to use our common mathematical optimization toolkit, like, gradient descent or any sort of combinatorial optimization algorithm. Instead, what we have to do is we have to rely on what is often referred to as surrogate model optimization. The idea behind this is I can evaluate this function I care about, the height function, as a function of watering, only through evaluations. What I can do is I can have a plant, I can water it, for a given set of frequencies, and I can measure, within a week how much taller it grows. And that's probably going to be, a noisy observation of this function, but I can still collect a few data points that would give me, for these particular values of water frequency, how tall does the plant grow. And what I'm going to do now is, based off of these data, I'm going to fit some sort of mathematical model to interpolate between these data points. And it's going to be a mathematical model that hopefully has, some nice properties, like it's differentiable or something like that, so that I can now perform traditional mathematical optimization on this surrogate model, this interpolation of the data that I've collected so far. Again, what's nice about this model that I'm using, the surrogate model, is it learned from the observations I already have. And so, of course, the more observations I collect, the better the surrogate model is going to become. And if my surrogate model is actually really good, then that's great, because maximizing the surrogate model is going to be approximately the same thing as maximizing the true objective function, which is, again, finding, maximizing plant height as a function of water frequency. Now, of course, this surrogate model that I've drawn here, this is one example surrogate model that could possibly fit the data that I've observed so far. And in fact, that there are many possible different interpolations that could seem plausible or reasonable to interpolate these 3 data points that I've collected so far. So instead, rather than just having a single, interpolation, I'm going to consider a distribution over possible interpolations, a distribution over surrogate models. In particular, so I'm going to have a posterior distribution over these surrogate models, and typically this is going to be a Gaussian process posterior distribution. Gaussian processes are nice distributions over functions, where we can often get posterior inference in closed form. This is why we like them a lot. The way to interpret this plot, if you've never seen it before, this is often referred to as a sausage plot. The idea is this blue line, the solid blue line here, is corresponding to the average, the posterior mean of all possible interpolations that I could have that interpolate these observations I have so far. So that would be like the average surrogate model. And this blue band is showing the 95% credible interval of different possible interpolations that I could have over here. So, for example, if I were to take a vertical slice of this at, say, the water frequency of 0.8, I would see that my 95% credible interval for what I expect the plant height to be at a water frequency of 0.8 be somewhere between 1 and, let's say, 1.9. What's nice now about having a distribution over possible surrogate models is I can now think about, when I'm now trying to think about what data should I continue to collect to make the surrogate model more accurate and therefore arrive at a better approximation of the optimizer of the objective function I care about, is I can use both the average surrogate model and the uncertainty to inform the decisions I want to make. So often what is done is we're going to use what is referred to as an acquisition function, which is going to be some sort of function of both the posterior mean and this uncertainty that I get to help guide decisions that I want to make. One common acquisition function is known as UCB, or upper confidence bound, where what I want to do is the next observation that I can should consider making, so the next water frequency that I should try to run to measure plant height, should be the value of water frequency that corresponds to the highest 95% credible interval under this posterior model that I have. Now, why is this a good idea? So basically what that corresponds to is if this this upper blue portion of the blue sausage plot over here corresponds to the 95% credible interval for any given value of water frequency, what I want to do is I want to choose the water frequency that maximizes or that finds the maximizer of that upper confidence interval. So that dotted line up there. Now, why is this a good idea? This is going to use the uncertainty information that I have to balance both an exploration and an exploitation of my design space. So if I have nearby, say, this point over here, this point in the middle, which is what I've currently observed is the best water frequency that leads to the highest or the tallest plants from what I've observed so far, it's very likely that water frequencies in a similar vicinity are also likely to lead to tall plants. And so if I search around that region, it's very likely that I'm going to continue to find good water frequencies that lead to tall plants. But at the same time, it's possible that if I were to measure water frequency in an area that I haven't explored much so far, say around 0.8, because I don't have a lot of information there, it could be possible that that is just happens to be the magic number that leads to the tallest plants possible. And so I would want to explore regions where I haven't collected data, a ton of data in the past. Looking at the 95% credible interval and choosing the water frequency that has the highest 95% credible interval is going to nicely balance that exploration and exploitation trade-off. Because I'm going to have a high 95% credible interval around known good optima, but also around regions where I haven't made a ton of observations so far. This is what it would look like, what a sample sequential optimization might look like if what I do is I now follow this procedure in an iterative sequential manner. So again, what I'm going to do is I'm going to start off with fitting this Bayesian surrogate model over the observations I have so far. I'm going to figure out where my highest 95% credible interval is. I'm going to choose that to be my next experiment, the next place where I think about evaluating plant height as a function of water frequency. I then collect a new data point. Turns out that this was a really good point to choose. It led to a taller plant that I've observed so far. And what I do now is I update my surrogate model. Updating my surrogate model, of course, means I'm going to now do a Bayesian update, which is going to update both the posterior mean, this blue line, but also update my uncertainty. Notice how my uncertainty is collapsing near where I have my new best observation, because now that I have made that observation, I'm pretty sure I know what's going on in the vicinity of that water frequency. I now am going to repeat this process, again, choosing my next experiment to be the 95% credible interval maximizer, but now, again, using this updated surrogate model where I have this additional data point. That's going to lead to this bump over here, which again is going to be somewhat near my existing optimum, but a little bit away where there's also some uncertainty about what the outcomes might be. And again, when I run that next experiment, I find an even taller plant with this new water frequency. I repeat this process over and over again until I get a surrogate model that looks something like what I have down here in the lower right-hand corner. If you notice in this surrogate model, I've now found water frequencies that lead to much taller plants than what I had initially. You also will notice that I have a lot of uncertainty over here for the lower water frequencies. I don't have a lot of observations between 0 and 0.5, but also according to this surrogate model, I'm pretty sure I don't need to make observations there. Under my model with 95% probability, I can see that none of the water frequencies down here would lead to plants that are taller than the maximum I've observed so far. So by using the sequential design approach, by using the surrogate model, I basically eliminated the need to measure a bunch of water frequencies that I have high confidence would not lead to good outcomes. So this is the framework of Bayesian optimization. It is often used as a sequential experimental design process. So here, I've used it on this sort of toy experiment of thinking about we want to maximize the height of plants as a function of their water frequency. Of course, in the real world, we might be interested in much more complicated problems. For example, like trying to find a molecule that maximizes binding affinity to some pathogen of interest. What is typically common when we're using this method of Bayesian optimization in practice is we're thinking about a design space that is typically a unit hypercube. So, right, if we're thinking about water frequency, right, this is just going to be, we're considering numbers between 0 and 1. If we're thinking about, say, trying to find molecules that maximize binding affinity, we need to think of some way of mapping the space of molecules into a unit hypercube. The surrogate model that we care about, so this thing that we're using again to approximate the true black box objective function, is typically a Gaussian process, which gives rise to these sausage plots that I've showed over here. And I'm going to go ahead and skip those last 2 points. With that in mind, I now want to get into the first part of the talk, which is thinking about how the geometry of our design space will affect the optimization performance of Bayesian optimization in practice. And one thing that is quite, which I'll talk about, which is quite surprising about this, is that I'm going to propose making a slight modification to the geometry of this Gaussian process surrogate model. That if we were just trying to model a static fixed data set, would be utterly useless, but actually makes the world of difference. We're now thinking about using this model in the context of sequential decision making. So again, we saw this example for what Bayesian optimization looks like when we are considering, very simple toy problems where the space that we have, like, say, 1 to 5 variables that we would be considering optimizing over. Of course, in practice, people want to now try to apply this to much more complicated design spaces, like the space of molecules, again, potentially in a drug discovery setting. Now we're thinking about really high-dimensional optimization problems, because trying to think about parameterizing the space of molecules, this is a really complicated design space that's, of course, going to, depending on the encoding you're using, going to be 100 or 1,000 dimensional. People have proposed using very complex surrogate models that go beyond, say, the typical Gaussian process surrogates that we talked about. But my colleagues and I were thinking about what would happen on these very high dimensional problems if instead we considered using simpler models rather than more complicated models. And we decided to, after a lot of experimentation, look to the simplest possible model that we could think of, which was going to be a linear model. So our question was, on these very complex and high-dimensional problems, as we're starting to think about benchmarking a lot of these complex surrogate models that people are proposing in the literature, we should, of course, really compare them against the simplest possible model, a linear model. Right. So, of course, because we're working in a Bayesian optimization space, we're going to be working with a Bayesian linear model, which, if you haven't seen a Bayesian linear model before, it's basically just going to look like ridge regression. That's going to be our dotted blue line, our average model. And then we're going to, of course, have some sort of posterior uncertainty around the outputs, which is accounting for our uncertainty in the exact set of coefficients that give rise to our linear model. Right. So you can again sort of think about it as standard linear regression. If we're using this as a surrogate model, we are now going to be assuming that our true black box objective function. So again, finding affinity as a function of the molecule is going to be linear in the covariance. In contrast, right, what I was showing before, the Gaussian process surrogate model can model any continuous function to arbitrary precision. And this is, so it's in many ways a lot more powerful and a lot more complex. And that's why it's often the de facto surrogate model for Bayesian optimization. Right. And a question that might arise is, do we need that complexity that comes from being able to model nonlinear functions for some of these problems that we're considering? And the answer is often yes. What I'm showing here is data from a 388-dimensional toy problem. And from this toy problem, I could consider 2 settings. One in which someone basically hands me a fixed static data set with covariates and responses, and I'm just trying to build a predictive model on this static data set and see the difference between what would happen if I used a linear model versus a nonlinear Gaussian process model to try to predict the response on some Blitzfeld data. And if I do that on this particular 388-dimensional toy problem, what I see is actually, yeah, I do need this additional complexity that a nonlinear model gets me. A linear model is actually quite a poor fit to the data. Right, I would get, say, an RMSE if I try to make predictions of about 0.6 with the linear model versus an RMSE of about 0.4 if I use the nonlinear Gaussian process, which again can model any continuous function at any arbitrary precision. Now, the same is true, or we see something similar that happens now if we consider not using these models again to fit a static data set, but again, to use these models in this Bayesian optimization loop where we're doing the sequential decision making of choosing new data points to acquire next to try to optimize this function. This is a standard plot on the right that you would see in the context of Bayesian optimization. If you've never seen one of these plots before, the easiest way to read it is we want to try to get to the upper left corner. Higher numbers are better, and also getting to those higher numbers earlier, so being further to the left is better. This green line again corresponds to the optimization performance we get when we use this Gaussian process model. So again, where we're using this model that can model any continuous function to arbitrary precision, we end up making pretty good optimization performance. I don't know what the maximum is in this particular function, but we're able to go from an initial value of about -0.25 to a value of like, say, about -0.5 or so. So make a pretty good amount of progress in 1,000 observations. Whereas the linear model, showing in blue, basically just flat lines. Basically, as we continue to run this optimization loop, we fail to find any new observations that happen to be better than what we started off with initially. So what we're seeing here is that linear models, not very good. They're not very good on these problems for supervised regression. They're not very good on problems if we're using them in Bayesian optimization. So my colleagues and I are going to propose a very slight modification to the geometry of this problem. So if we're given d covariates, what we're going to do is we're going to introduce just one single new covariate that can be, of course, derived from the covariates that we have access to. And in particular, this additional covariate that we're going to be introducing is going to be 1 minus the squared norm of all of the other, of the Euclidean norm of all the other features that we have access to. That's it. So this additional covariate that sometimes contains no new information because it can be derived from all of the other covariates. What happens now if we just include this one additional feature? When we're thinking about supervised regression, it makes no difference, which kind of makes sense, right? We're only adding this. We have this one feature that's going to make our model now nonlinear in the original set of covariates, but barely nonlinear because it's just one derived feature from all these other covariates. So we see that if we do supervised regression, we basically end up with almost no additional performance gain over what we have from the linear model, still pales in comparison to the highly nonlinear Gaussian process that we're using. However, this is now where what really surprised us is that if we now use this new model on this transformed space in the context of Bayesian optimization, we see a massive performance improvement over the linear model on the original set of covariates. Such a massive improvement that we're now seeing as good, if not better, performance in terms of sequential optimization than what we got from the GP that was, this, again, highly nonlinear model, this much more complex model. So again, this one small change that we made to the geometry over input space, almost no effect in the case of supervised regression, massive effect in the case of Bayesian optimization. So what explains this? Why did such a small change make a huge difference between these two types of problems? Well, think about what this additional feature is providing in the case of supervised regression. Let's imagine that our data happen to be drawn uniformly at random from our input space, which again, I said was a unit hypercube. I'm going to scale this unit hypercube a little bit rather than being, say a standard unit hypercube, which would go from 0 to 1 in d dimensions. It's going to go from -1 over square root d to +1 over square root d. So, right, if my data are uniformly distributed in this hypercube, which again would imply that, for each of the coordinates, each of those coordinates would be, IID uniform for x1, for x2, and so on. By the law of large numbers, what this means is that the squared, if I were to sum the squared values, there's a typo here, that should be the squared norm over here. The sum of the squared values of each of my coordinates, by the law of large numbers, should concentrate around a fixed value, which you can see here from a very simple simulation. So this extra feature that I have, as the dimensionality of my space increases, effectively becomes a constant, because the Euclidean norm of my features is basically going to concentrate around a fixed value in high dimensions. So this is providing actually zero information in these high dimensional spaces. It's not providing any new additional data or information that we can regress on. But now let's think about what's going on in the case of Bayesian optimization. Why would this make such a big difference? Well, first let's think about what's going on if we use a linear model on our original set of covariates. Linear functions are monotonic, right? And they're not only is this blue line, the average linear model, monotonic, but also if I'm being, Bayesian about things, and I also have this credible interval around the predictions being made by this linear model, that 95% credible interval is also going to be monotonic. What that means now is if I'm now choosing the next design to be the design that has the largest 95% credible interval, it will almost surely live on the boundaries of my space, because if I'm being monotonic, I should just basically go to the edge of my space. And we actually see that in practice play out. What I'm showing over here on this bottom plot is when I'm thinking about every acquisition that I'm making in this sequential optimization, I'm plotting the percentage of dimensions, so the percentage of my covariates that are live on the boundary, so either -1 or +1 for every iteration of optimization. And so I'm finding that it's not just that my data happen to live on the boundary, it's even worse than that. Typically within Bayesian optimization, the data points happen to live on one of the corners. 100% of the covariates are at their extremal values. So when I'm using a linear model, in the case of Bayesian optimization, naively like this, often what I'm doing is I'm basically just doing some sort of combinatorial optimization over the corners of my design space, which isn't actually going to be too useful, especially when I'm thinking that my actual objective function of interest is nonlinear. What happens though, as I introduce this additional feature here, again, if my data are from the unit hypercube, and again, a unit hypercube that is scaled to be proportional to the dimensionality of my input space, then the norm of my inputs is going to concentrate around a fixed value. So in other words, this additional mapping that I'm doing is going to be mapping my original set of covariates from the hypercube in d dimensions to the unit sphere in d+1 dimensions. If I now think about a linear model that it can only act on the unit sphere, I no longer have this pathology that's due to the monotonicity of my linear model, right? I can't simply increase the output of my linear model by scaling the particular data point of interest, because I'm restricted to be on the unit sphere. Scaling no longer applies. So now that I have basically I am still using a linear model, but I no longer have this pathology that my linear model is going to force my acquisitions to always live on extremal points. And in fact, what we find in practice is that often now with this change, we tend to, the Bayesian optimization loop will tend to explore points that live in the interior of the original space, not just the corners. We actually ran this algorithm now. Again, this is very simple idea of mapping our data from the unit hypercube instead onto a unit sphere, and then just applying a linear model and doing Bayesian optimization. We applied this the simple paradigm now to a common molecular design benchmark, where again the molecules are typically encoded in a way so that they live in the unit hypercube in a 256-dimensional space. And what we found is that we were often able to actually massively outperform some of the state-of-the-art methods that people had proposed for this problem, again, simply by using a linear model. So to summarize this first part of the talk, subtle changes to the geometry of linear models can have massively different effects depending on the outcome that we want, that we're trying to achieve. Are we just trying to achieve simple inference on a static data set, or are we trying to, again, perform sequential decision-making, such as in the case of Bayesian optimization? In the case of just simple supervised regression on a fixed data set, embedding our original design space onto a sphere has basically no effect, because our data are very close to lying on a sphere already. In the case of Bayesian optimization, though, in the sequential decision-making problem, mapping our data onto a sphere is actually very necessary in order for this algorithm to run correctly, because it removes this pathology of the monotonicity of the linear model. Our acquisitions aren't going to be confined to the boundary, they're going to be able to explore the interior. I basically explained why this simple mapping allows linear models to not just completely collapse towards this pathology. I can't yet explain why they're so effective at these particular tasks. But in future work that my current students and I are currently ongoing with, we're trying to establish a connection between linearity and locality, and thinking about, does this model basically allow us to perform Bayesian optimization within a space where, say, a first-order Taylor approximation might be a very reasonable approximation of what our true objective function is. Before I move on to the last part of the talk, are there any quick questions about that?
Excuse me, I'm a little confused about why adding the normal into the data can achieve so much improvement. I'm still a little confused about it.
So confused about why mapping onto the sphere can lead to such an improvement, or
yeah, that's why adding the 1 minus the norm.
Yeah,
it can achieve so much.
right. So 1 minus the norm isn't necessarily the only like this is a sufficient but not necessary condition to lead to performance. Basically, what we need to do is we need to decouple direction and scale when we're thinking about using a linear model for these sequential decision-making applications. So we basically need some, like if I am thinking about a linear model acting on a unit sphere, what the linear model basically becomes a function of cosine similarity on a unit sphere because I've removed the effective scale altogether. Whereas if I'm not operating on a unit sphere, I can basically always increase my linear model by just increasing the scale of points. So I have to basically remove this effect of scaling from the linear model. And then in a high dimensional space, it will only become a function of the cosine similarity of the data points that I care about. I'm happy to chat more about this offline to clarify things. I see there's a question in Zoom.
I think it was just a slide.
Oh, okay, gotcha. All right.
Yeah.
In the interest of time, I'm going to move on to this last part of the talk, but I'm happy to again answer more questions. Oh, was there a?
No, I'm just thrown by the x's originally being IID, but then you're adding in the spherical component, which is obviously dependent on the other x's. So you're just adding it as another point.
So this would be I'm assuming that the covariates themselves are IID uniform, which is of course an assumption that's probably for most high-dimensional problems that's maybe an oversimplification, but in general, what we often find is that like on any sort of high-dimensional data set, it's very common for the norm of my covariates to be very concentrated around a specific value. So that would be this would be something that we've generally found on a lot of high-dimensional data sets that we've looked at. I'm not sure I answered your question quite there.
No, I think you did. You're saying it's dependent on the sort of data that you're looking at, really.
Exactly. Yeah. Okay. So I will just, in the interest of time, move on to the second part of the talk on decision-aware model selection. So I guess one step that is missing from this optimization loop that I've talked about so far is, again, I'm assuming that this distribution that I have over functions, this Gaussian process distribution, was sort of just handed down from on high to me. But of course, if I want to actually use this distribution, like any set of distributions, there are usually a number of hyperparameters that we have to select over. In the case of Gaussian processes, there's often things like the signal to noise ratio or the intrinsic length scale that I'm using to interpolate with my function. So what I talked about in this optimization loop originally was thinking about propose an experiment, collect data, and update model. As part of this updating model, there's often going to be this additional model selection step, where what we're doing is we're thinking about certain design decisions that might be present in our model. So this would be choosing, again, specific hyperparameters like the signal to noise ratio or the length scales, intrinsic length scales of my model. And I'm typically going to be choosing those design decisions to optimize some sort of model selection criteria and doing this at every iteration. So for example, one potential example where this might come up is, again, thinking about there's one particular instance that we looked at, which is maybe a little bit of a toy instance in the case of Bayesian optimization. But this is a case where what we are going to do is we are going to have a model selection problem of we want to try to choose a core set of data to approximate all of the data that we're conditioning our model on. This is a common thing to do with Gaussian process models when you're working with very large data sets. Often in the case of Bayesian optimization, that's generally not the case. Like typically, the number of acquisitions that we would be trying to fit with our Gaussian process would be on the order of 100 to 1,000, which is totally fine. But just kind of for illustrative purposes, what we're going to do is we're going to try to try to illustrate this technique that we want to have. We're going to introduce this additional model selection complexity step, where what we want to do is we want to now select a core set, so a much smaller kind of fake data set of what are often referred to as inducing points, to approximate our true set of observations we have so far. Typically, we choose the core set to be have m, which is a lot less than n fake data points in it. Again, typically it's used for scalability, but for now we're just basically going to be using it for illustrative purposes. This is an example of what the output of this approach of using a core set would look like. So each of these stars over here represents an observation that I've collected so far. But again, rather than now conditioning the model on every single observation, the first thing I'm going to do is I'm going to now choose a fake data set with many fewer data points. And from that fake data set, I'm now going to condition my model on that fake data set, which will hopefully be a reasonable approximation of my model condition on all of the data. Each of these vertical lines corresponds to at least the x value of the fake data points that I'm introducing. Here you can see that I'm introducing 4 fake data points, and that's going to lead to now this blue posterior distribution, which is effectively the same as the posterior distribution I would have gotten if these 4 fake data points were the actual observations that I had. Again, this is a technique that's typically used for scalability. This is obviously a very toy and illustrative example, but we'll see why this step might be a problem for Bayesian optimization. So typically, when we're trying to think about how do we choose such a core set to describe the data that we have so far, there's many techniques that people have proposed toward choosing a core set. A lot of them rely on techniques from, say, fields of variational inference or other related approximate inference fields. But the high-level idea is that the core set points that we're going to be choosing are often going to be points that describe the data that we've collected so far well, which makes a lot of sense, right? If we're trying to model or approximate the posterior distribution, given a set of observations, we would probably want to choose fake data points that look similar to those observations we've made so far. So the course, going back to this example, we notice that all of our true observations tend to be on the left half of this graph, and we only have a couple observations on the right half of this graph. So what's going to happen is these fake data points, this core set that we choose, most of those 3 out of those 4 points are going to lie on the left half of the graph, where we have a lot of where we're dense in the data that we have, and only one of these core set points is going to lie in this data sparse region over off on the right. Now, again, this would make sense if what we're trying to do is just approximate the posterior distribution as the final product in and of itself. But of course, what we want to do is we want to use this posterior to think about what is optimal data to select. And I'm going to argue that this way of choosing our core set points is actually quite suboptimal when it comes to thinking about data acquisition. To demonstrate that, what I'm plotting over here on the right now is going to be that 95% credible interval as a function of x, where in this very hard to see light cyan color, this would be that 95% credible interval if I had chosen to use my true posterior distribution over all of my data points. And what I'm showing over here on the right is what that 95% credible interval, or sorry, in the red, is the 95% credible interval if I'm using this approximate posterior distribution from the core set points. What we can see is even though I can probably think that this posterior distribution over on the left is a pretty good approximation of the posterior distribution itself, this functional that I'm trying to compute from that posterior distribution, this 95% credible interval, is maximized in totally different places from my approximation versus my actual true posterior distribution. So again, if I'm using this, if I'm using this to choose what data point I should acquire next, with this approximation, I'm choosing a data point that happens to lie in this region of data where I already have a lot of observations. It's not going to be very useful. The decision I'm making with this particular approximation is quite poor. So rather than following what would be a standard model selection criteria, which would be let's choose core set points to describe the data we already have, well, instead we want to choose a model selection strategy that is aware of the sequential decision-making process that we have in play. We want to choose a model that yields an approximately optimal data acquisition, as opposed to one that just describes the data we have so far well. And so the way that we're going to do this, I'm going to skip over some of the details, but I'm happy to talk about them more offline, is if you notice this procedure that we have as part of our Bayesian optimization loop, there's sort of these two nested optimization problems that we have. The first the second optimization problem, this is the data acquisition optimization problem. This is saying choose the data point that has the largest 95% credible interval. This first optimization problem up here, this is going to be our model selection optimization problem. So this is going to be choosing the core set points, that optimizes some model selection objective. And having these as two separate optimization problems that aren't speaking to one another feels a little bit suboptimal. So what we want to do instead is we want to take those two optimization problems, one of which is choosing the core set points, one of which is choosing the next data point to acquire. We want to merge them into a joint optimization problem. We're simultaneously choosing the core set points as well as the next point to acquire. And we're going to be using a joint objective function, which we call the ULBO, which stands for the expected utility lower bound. I'll explain in 1 second. So this joint objective, this expected utility lower bound, is derived using techniques from variational inference for model selection, but also from decision theory for data acquisition. The derivation, for those of you who might be familiar with variational inference, very much follows like a standard variational objective and kind of turning the crank through some of the standard techniques that exist. What we ultimately arrive at is a joint objective function that looks very similar to what we had before. It's going to be a combination of something that looks very similar to the objective function that we had for data acquisition. So again, finding a point with a really high 95% credible interval, plus the objective that we had for model selection. So again, some sort of typically loss function that would say choose core set points that describe the data that we have very well. But if you notice, rather than now having these as two separate optimization problems that we're performing separately from one another, we're now thinking about choosing both the new data point and the core set points to maximize the sum of these two. So we can actually have some trade-off between core set points that describe our data well and also what would lead to good acquisitions. If we now run this process in practice, again, what I'm showing over here would be the set of the core set points that we would have gotten if we had used a standard model selection objective. So one that only cares about best approximating the data we've seen so far. And again, that leads to over in red, this very suboptimal data acquisition that looks very different than what we would have had if we had actually used all of the data that we had access to. If we now use this new model selection strategy that we proposed, this decision-aware model selection strategy that is simultaneously considering the data acquisition along with the core set point selection, what we end up with now is a different set of core set points. Before we have the ones that are over on the left, which again are going to be very dense in the left part of the data region and a little sparser, to this new set of core set points that's going to be more evenly spaced throughout the input space, what we're seeing over here on the right. And if, again, we were just thinking about traditional model selection, this would not be an optimal set of core set points to describe data that we have so far, because going back one slide, we have no data in this regime of our input space. So we would not want to waste one of our precious core set points to describe what's going on over there. But it turns out if what we care about is, again, making this optimal decision of where we should acquire data next, it's very useful to put a core set point there. That now leads to a 95% confidence interval that's maximized very near to where our true 95% confidence interval maximizer is. The red and the cyan lines overlap a lot more on the right plot. And of course, that's on a toy problem. If we actually consider this in practice, what I'm showing here again is a set of common benchmark problems that people use for Bayesian optimization. Again, the goal is to get the higher line earlier here. The black line corresponds to sort of the standard approach where we're doing separate model selection and data acquisition using sort of what would be like the sort of naive version of model selection. And then in the purple over here, what I'm showing is this joint strategy for simultaneously considering model selection and data acquisition in this decision-aware way. And pretty much across all of the benchmarks we considered, we found that this joint optimization generally led to much better Bayesian optimization performance. So to summarize this part of the talk, the key takeaway here is that the objective that we use when we're considering model selection, so typically something like what would be like maximum likelihood, if we're just care about describing our data well, it has very disparate effects when we're considering, again, supervised regression, sort of standard static problems versus Bayesian optimization performance. Again, performance in this adaptive sequential decision-making setting. So when we're just thinking about standard model selection, again, what we want to do is we just want to choose a model that maximizes potentially an approximate notion of our marginal likelihood of unobserved data. But now in the sequential decision-making setting, where again, we don't just care about describing data we've collected so far well already, being able to jointly optimize the model and the downstream decision together, which creates now potentially a model that is actually quite poor at describing our current set of data. This might actually be the optimal decision that the optimal choice that we want to make. Even though it doesn't describe our data very well, it will lead to better downstream decisions. So again, this is just an initial case study on kind of this simple, maybe contrived example where we're considering trying to place a core set of points to approximate our true full data set. In practice, you probably wouldn't want to use this algorithm. So what we are now considering is an extension of this beyond just this core set placement problem, but thinking about how to extend this recipe to other model selection problems, like choosing the signal to noise ratio, choosing the length scales of the model that we're trying to use. So just to briefly in the last minute or so talk about where I'm going with this and future work. Some sort of immediate next steps from these two projects that I talked about. So in the first project, which was thinking about linear models on spherical embeddings of our input space, I think kind of the obvious next step is understanding the unreasonable effectiveness of linear models on Bayesian optimization problems, of course, after we do this geometric transformation to map our data points from, say, a unit hypercube to a unit sphere. And in the second part of the talk, which is focusing on model selection, I think the immediate next step is to apply joint model selection and acquisition optimization strategies to other problems beyond this core set problem. Again, kernel length scales or other common choices that people would often require model selection for in the case of Bayesian optimization. But I think kind of moving forward beyond these immediate next steps, kind of where I see a vision of this going is that a lot of problems that we care about in terms of scientific discovery, thinking about things like designing new materials, designing new drugs, they can all be formulated as optimization problems. And it's definitely a setting where people are very interested in applying Bayesian optimization to many of these problems. Of course, the complexity of these problems, thinking about working in these very high dimensional spaces where we have lots of constraints and, where we have to think about mapping, these often discrete structures like molecules into, potentially continuous representations of features. This poses a lot of challenges on these like frontier problems. And many approaches that people have tried to propose for optimization on these really challenging, important scientific discovery problems feel a lot like alchemy, where there's a lot of specific ingredients that you have to tune just right to get reasonable performance. Otherwise, things fall apart. For example, what I'm showing here on these graphs come from a paper written by some of my colleagues that were looking at using neural networks on some materials discovery applications where the goal is to try to find new materials for carbon capture. And what they found is that making very small changes to things in the neural network architecture when trying to run optimization performance, say like changing the initialization by a small amount could lead to wildly different performance. And tuning these values right now requires a lot of guess and check without a lot of real understanding of what's going on. And I think part of the problem here, again, is because all of these design decisions that we're making about the models, where they're coming from is from our experience on fitting static data. And if we were to instead take a decision-aware modeling approach, we're really taking into account the fact that we want to be applying these models to sequential decision-making problems. And if we can, again, sort of formalize what model design and model selection means in this setting, it could help hopefully change what is currently right now a little bit more of a dark art and alchemy into more of a rigorous science where we can actually make more progress in some of these important frontier problems. And with that, I would like to thank a whole host of collaborators, especially students Colin and Donnie, and collaborators Natalie and Curie, who were the first authors on these works and really drove out a lot of the research. And with that, I'll take any questions.
One question online, wondering for the first part of the talk, if there's anything special about the L2 norm, or if you did any comparison with other types of nonlinear transformation, and if this gain in performance depends on the underlying geometric properties of the data set of the problem.
That's a very good question. So the as far as the L2 norm being special, I think the answer is yes in that case. And the reason I think the L2 norm is special is because, right, if we're thinking about the L2 norm, we're mapping our data onto a unit sphere. If I think about a linear model, I could think about a linear model. It could also be considered to be a kernel model where the kernel function is going to be the linear kernel x transpose x prime. If everything is on the unit sphere, x transpose x prime is now just going to be the cosine similarity. And so I think that by using the if we were to use a different norm, then things aren't going to be mapped to the Euclidean sphere. They'd be mapped to something different. We would no longer have, say, like a kernel that would be a function of cosine similarity. It would be something that is conflating both direction and scale as well. So I do think the L2 norm is quite special here. That's a really good question. As far as does this depend on the geometries of the problem, I think the answer is a little bit yes and no. I think that obviously, the answer is yes, because there's no magical one-size-fits-all approach. And so I'm sure if everyone in this room, if we all spent 30 minutes brainstorming together, we could easily construct an adversarial example where a linear model on a sphere would be absolutely horrible and be the worst possible model that we could use. But also at the same time, I think one interesting thing about Bayesian optimization in particular, right, is that it's not as if we have, here's a distribution of data. We're adaptively choosing the data we have access to. We're essentially constructing what our data distribution looks like through this acquisition function. And I do think that there is, without this mapping onto the unit sphere, there is a definite pathology that gets introduced that regardless of whatever our function happens to look like. So yeah, that's a little yes and no for does the geometry actually matter? Great.
So for your second part, will you simultaneously optimize the model selection and data acquisition? Do you have a fixed prior, or do you also update your prior?
Very good question. We tried both. We tried both having the fixed prior is what we did for sort of our nice experiments where we're trying to keep we're trying to be very isolated in what we're measuring, but in practice we also it was actually like a joint optimization in terms of both choosing the core set points, choosing the acquisition, and also choosing the hyperparameters associated with the prior. All three of those were happening simultaneously, and that seems to be beneficial as well. So yeah, there's a lot more in there that we want to unpack in future work.
Okay, so when you update the prior, I suppose you will have a better performance?
Yes, yeah, exactly. Updating the prior seems to be necessary to squeeze out the most possible performance.
Okay, and for the first part, I think it's a nice idea to consider X tilde.
Yeah.
So when you add then to 1 minus L2 norm of X, would that also create a new potential issue in a sense? If my original data X1, Xn are independent, but when you add this, you actually
Right.
with a collinearity issue.
Yeah, right. There. Now, if we add this feature that is basically, a composite feature of all of the other covariates that I have, right? Then I will have, of course, some dependency between all of my covariates. I don't think it necessarily creates a collinearity issue because it except in like, probably what would be like extreme adversarial cases, just because it is a nonlinear transformation of all of my covariates. But yeah, it definitely creates a dependency. I think in practice, we found that it didn't produce any huge issues, again, because I think in like a supervised regression problem, for the most part, that covariate just ends up being effectively a constant or is typically just thrown away.
Okay, so creating that additional column is trying to capture some geometric features.
And in some sense, it's actually like, and this is what I think is kind of wild, is like from just like a standard modeling perspective, it's that additional feature is basically doing nothing. But when we are now doing Bayesian optimization, it's basically forcing us to lie on a sphere. And so it's effectively, yeah, from just a like pure modeling perspective, it's not really doing anything, but it's acting as a hard constraint when we're considering like optimizing over the entire space.
So I wondered if you say rescale your each component by divided the norm.
Yeah, right. Okay. Yeah. So that's a very, yeah. So yeah, the question would be like, right, like if we divided each of our components by the squared norm, which would be another way of constraining our data to lie on the unit sphere. We tried that experiment, and that also produces beneficial effects over the linear model. It's not quite as nice as introducing this new feature because now we are removing one dimension of information. Like we're going from what was a d-dimensional problem to a d-1 dimensional problem by removing the scale component. So adding an additional feature, so going to d+1 features, allows us to retain all the information we have. In practice, actually, in the paper, we're doing a slightly more complicated transformation called the inverse stereographic projection to go from the arbitrary covariates to the unit sphere. It's a slightly more complicated formula, but just has a fewer nicer properties. But yeah, like many different mappings from to the unit sphere will remove this pathology.
Okay, thank you.
Yeah.
Nothing. There's nothing else online.
Question on room.
No, there was one, but
Oh.
I read it already. So
Oh.
I think we're okay.
Thank you, everyone.